Hey everybody, this is Mr. Schultz here with you, and today we're going to take a look at 812, how can I describe growth? And specifically we're going to talk about compound interest, which we just barely started to hit on yesterday with the baseball card question. So let's take a look at what this is. So far in this course we have studied simple interest, which only pays interest based on the amount invested. It might be useful for informal loan arrangements between parents and children or between friends. However, banks and other financial institutions calculate interest in a different way. They commonly use what's called compound interest. You will learn more about this type of interest in this lesson. All right, and then the bottom part here just basically talks about what we talked about in the last lesson and finishes by that growth of 50% from the baseball card. So we're going to look for what patterns do we see and how do we show the connection. Let's take a look at the first problem. So the first problem is 8-13. It says this: Miss Hartley won $20,000 in the lottery. She decided to spend half of it right away and invest the other half of the money for her retirement. The interest rate on the account that Miss Hartley chose is 5%. She calculated that after 10 years, based on simple interest, her account balance would be $15,000. However, the banker told her that after 10 years, the account balance would be $16,289. A financial advisor explained to her that the bank is paying her compound interest, which is what we talked about in the introduction. That means that a bank is calculating the interest each year on the total principal and any interest she has earned so far, rather than just the original $10,000. So if Miss Hartley leaves money in the account for 30 years, her $10,000 will grow to more than $40,000. So just talking about this sentence here, again, that means that the bank is calculating the interest for each year based on the total. So it's calculating the interest based off your total money in the account instead of just the original $10,000 is all that's saying. So let's see what this problem asks. So to help see this difference, they made these two charts. So they've got the simple interest and the compound here. So take a second. Explain how you see interest growing in the simple interest chart. So on this left side chart in problem 8-13, explain how you see the interest growing in the table. Take a second and take a look at that. Okay, so bringing it back in here, I see this kind of flat number growth here. It's growing by $2,500 each time. It's just adding $2,500, $2,500, so on and so forth. Okay, so it looks like it's adding $2,500. So on your paper, you'd want to label it, you'd want to label it 8.1.2. We're on problem 8-13, and this is problem number A. And here we're just saying that it's growing by $2,500 every 5 years. Now in part B, which is going to be right down here, it says this: explain how the interest grows in the compound interest table. Let's take a look. Now you might see something that's a little bit harder to find here. When you go up on each of these sides, not on each of these sides, but each row, the first row you get a change of $2,763, so a little bit more than that $2,500. This next change, that changes to a different number. $3,526 is what that one goes up by. And then my next one goes up by $4,500. So it's changing by different amounts each time. So it doesn't really seem like it's changing by a consistent addition or subtraction. So if we think back to our work with sequences, we had arithmetic ones that went up by adding and subtracting. We also talked about these geometric sequences went up by multiplication. Let's see if we can use some of those skills to find out what is happening here. So in a geometric sequence, you would take the second term and divide it by the first term. So in this case, you would end up with $12,763 divided by $10,000. 1.2763. And then, so this is going up by 1.2763. Then if you do that again here, you get that same decimal, 1.2763. So what this is looking like is this is growing by multiplication. By multiply by 1.2763, and that will get you each of your following numbers. So my last question here, part C, says this: after 30 years, how does the simple interest balance compare with the balance in the compound? Well, it's way less. You've got almost $20,000 more. So it's way less. So long story short, if you're investing, you like compound interest. If you're borrowing, you don't like compound interest because it's going to be more, but you're investing, you like that it's going to create more money for you. Let's take a look at the next problem, 8-15. All right, so we're going to skip problem 8-14, which the setup there was about this girl named Mariana, and saying that her grandfather invested $500 the day that she was born into a college savings account. So using that information here, it says that she is curious about how much money will be in her account when she is 18 and graduates from high school, because that's when she'll need it for college. So she went back to the table that she had created and looked at the numbers in the first two columns, the years and the balance. She noticed a pattern that she thought she could rewrite a shortcut. Study the table and her work. So let's take a look at this table here. So we see you've got this 500. She multiplied it by 1.05 to get this number. But then she said 500 times by that 1.05, which is the same thing as this number, times that by 1.5 got us there. Times that by 1.5 will help us get to the next one. Let's see this on the next, how this relates to the problems. All right, so part A says, as Mariana works down the table to fill in the entries, what changes in Mariana's calculations? What patterns do you see? Well, things that I noticed would be this. So I noticed that the number of years is equal to how many times multiplied by 1.05. So for example, in year 1, there's 1.05. In year 2, there's 1, 2. In year 3, there's 1, 2, 3. So I'm guessing that in year 4 that there's going to be 4, 1.05. So in Marian's calculation for 2 years, what does 500 times by 1.5 represent? What is 500 times by 1.5 equal to? Well, let's find that out here. It looks like we've got it in the table. It's just this number right here. So 500 times by 1.05 is equal to $551.25. So really this in parentheses here is equal to the number that she's finding in each of these balances. So she's basically taking the previous balance and then multiplying it by that. She's taking the previous balance and multiplying it by 1.5. So how could you rewrite Mariana's balance at the end of any year in terms of the principal, which is $500. So previously when we've talked about stuff like that and we've talked about it in sequences, we just said, well, we need the previous term to know what to multiply by 1.5. But what if you wanted to find out year 18? Well, to do that now, I have to create all of these other years until I get all the way down eventually to year 18. But what if I want to just go straight to that because I'm lazy and I don't really want to figure out every single year up until year 18? Is there a way that I could do that? Well, as I mentioned, it looks like you would just say you're multiplying 1.5 18 times. So I'd take that original $500 and I'd multiply 1.05 18 times. Now that's not times by 18. That's saying 1.5 times itself 18 times. So I have to write 1.05, 1.05, 1.05, and I have to do that 18 total times. Okay? So, based on this pattern, describe how you'd find Mariana's balance after 18 years without first finding her balance at the 17 years. Well, that's exactly what we just talked about here. We just have to say 500 times by 1.05, and we have to do that 18 times. So let's see what that would turn out to be on our calculator. So when we plug that in, we say 500 times by 1.05, we're multiplying 1.05 18 times. So I have to type in times 1.05 18 times. You should get the number of $1,203.31 if you round it cents. Okay. Now this is a pretty inefficient way to do this. Multiplied by 1.05, multiplied by 1.05, multiplied by 1.0. Nobody really likes to do that because this is only 4 of them. 1, 2, 3, 4, and I need to get 18 of these. Whoops, sorry, not 18 here. This should be a 500. 500, which is our original starting principal balance that her grandpa donated. And there's only 4 of these, and I need to get 18 total of this. Let's see if we can use some math to get it to be faster. And of course, we can. It is on problem 8-16. It says, the pattern you describe in words in part C of our previous problem can be written as symbols using an exponent. For example, 4 times 4 times 4 times 4 times 4 can be rewritten as 4 raised to the 5th power. This is what's called an exponent. Here, 4 is the base and 5 is the exponent. So 4 is going to be the base, and then the exponent is going to be the small number. That is going to be 5. So great thing to write down there. 4 is the base, 5 is the exponent. So the small number is the exponent, the big number is the base. And it's read as 4 raised to the 5th power, or 4 multiplied by itself 5 times. So I've got 1, 2, 3, 4, 5 of these. That's why I'm multiplying it by itself 5 times. So we can do that in the same thing in the previous problem by saying that her grandpa's original investment of $500 is being multiplied by that interest rate of 1.05, but that's happening 18 times. 18 times. So that is our expression here to represent this. So now this is much easier to write and type into your calculator, because instead of having to write 1.05 times 18 different times, I can just write 1.055 raised to the 18th power. So if you try this on your calculator, a common key for this, and especially if you're going to use a computer to type this, is this caret key. It looks something like this. It is above the 6 key. And so generally you have to click Shift 6, and that'll get you this kind of caret key that'll be able to do this. So if you're going to type this into Google, I would say 500, and then I'd say the multiply key, so probably X, then I'd say 1.05 caret key to the 18, and that should get you that number of $1,203.31. Okay? So our very last thing here says this. I'm going to label this as part C. A comic book is purchased for $6. It is resold 7 times, and each time it's resold, the seller charges 15% more than he or she paid for it. So, how could we rewrite this? Well, thinking back to our previous problem with Mariana. In fact, I'm going to give you a second to think about this. How would you rewrite this and find out how much this is going to be without multiplying 7 times by using an exponent? So take a second to think about that. All right, here we go. So the original, that kind of principal investment was $6, and then they're selling it for 15% more than the previous. Well, so they're selling it for the previous value, which is 100%, and then plus that 15. So if they're selling it for that, they're actually selling it for 115% of the original cost, which is equal to 1.15. Now, that's being resold each time that's being sold is 7 times. So I'm going to raise this to the power of 7 because I need to multiply 1.15 7 times itself 7 times. So to plug this into your calculator, I really think you should practice this, especially if you're going to use a keyboard, if you want to use some sort of a calculator. 6 times by 1.15, and then use that caret key again, raised to the 7th power. And that tells you that your final cost, the final cost if somebody bought this for, is $15.96. So the original comic book was bought for $6, but it increased in value because somebody bought it for $15.96. So all this is summarized in the math notes here about exponents. So the big thing here is that this bases and exponents can be used to rewrite expressions that involve repeated multiplication. This is your key thing. Repeated multiplication, which is exactly that phrase we used when we talked about geometric sequences. We said it is repeated multiplication. So what that means for you is this. It's a convenient way to write that instead of having to keep multiplying, keep multiplying, keep multiplying. So the expression a to the n is written in exponential form or an exponent form. The base a is the factor that's raised to the power. The exponent n is called the power. or the exponent. So I remember in math class that these kind of variable approaches always kind of threw me off. So here they gave us a written example here. A to the n is the same thing. It can be written like 2 to the 4th, where a is equal to the base, or in number form, 2 is equal to the base, and in the variable form, n is equal to the exponent or power, whereas 4 is equal to the exponent or power, as we look at it here. So, and 2 to the 4th means 2 times itself 4 times. So 2 times 2 times 2 times 2. It's repeated multiplication. That's a bunch of everything. Have a great rest of your day.